Okay. Let's continue with the topic of impulse and momentum, which is the third method to solve the equation of motion. You saw the Newton law, and then you saw the work and energy. And today we're going to talk about impulse and momentum. And we are still in the topic of, in category of particles. And this is sort of the last topic in category of particles. And you saw I posted the note for the Friday lecture. Please take a look. And if you have time, I indicated which section from your textbook you should start reading. Maybe if you read it in advance before your lecture, that would be great. If not, just take a look. And then on Friday, we will start with we move from particles to rigid bodies, basically. So what is impulse and momentum? We talk about it briefly, but let's do a quick review. Basically, we said F is equal to ma is our main formula, always. You saw for work and energy, we convert this to a new formula, but everything was based on F equal to ma, the Newton law. If I rewrite this equation as F equal to m instead of a, I write its definition, which is dv over dt, the rate of change in velocity as a function of time. And if I rewrite it now as f dt equal to m dv, I'm getting this differential equation. When we say differential equation, it means the time or other parameters like velocity here are very, very small. That's why we call them a differential equation. But if we do an integral, and let's say we always start from time 0 and we get to a certain time, delta t, 5 seconds, 10 seconds, whatever. And velocity, let's say we start from velocity 1 and go to velocity 2. Since F is constant, mass is constant, then from here I can rewrite it as F multiplied by delta T is equal to mv2 minus mv1. All right. So this first parameter here, we call this one impulse. So force multiplied by time. You remember force multiplied by displacement, we call it work. Force multiplied by time, we call it impulse. Mass multiplied by velocity, we call it momentum. The bigger the mass, the bigger the momentum a particle has. Or the faster it moves, it means the higher or the greater its momentum is. So we call this one, we show it by G, so it's going to be G2. Or let me just write down momentum. So let's simplify it and just some, like show it by formula. I can write F multiplied by delta T is equal to G2 minus G1. And G is just a parameter we use for momentum. Or I can write it down as G1, right, is equal to, am I right? I write it down here. G2 minus G1. Yep, G1, if you just move it to the left side, F delta T is equal to G2. And this is called the principle of impulse and momentum. Whatever momentum a particle has, plus we apply a force in a certain time. The longer we apply the force, the bigger this impulse is going to be. And then we get to a new momentum, which is called G2. So momentum is more like energy, but you remember for energy, we had a definition half of mv squared, right? That was a different basically concept, which we call it energy. If we just simply multiply mass by its velocity, we call it momentum. So what if there is no force, or the forces cancel each other? So if F equal to 0, then we're going to have G1 is equal to G2. And this is what we call it, the conservation of momentum, basically. Similar to conservation of energy, which E1 is equal to E2, is momentum 1 is equal to momentum 2. Okay, so this is all the formula that we have. Let's solve one very simple example. Let's say I have maybe a mass here, like a particle A, and then over here, let's say I have a particle B. So this is then A, and this is B. And let's say they are moving on a straight line, just for simplicity for now. But in general, they can move in any direction. Maybe this B, let me write it. Okay. So let's assume that VA has a velocity going that direction, and VB has a velocity coming opposite direction. So they collide to each other. And they don't have to necessarily be on opposite direction. The same things, let me draw it again. Oops. So the same things this time. Can I get rid of that? Yes, that's good. So let's say VB going to the opposite direction. Let me write it down. This is VA, this is VB, or this is VA, and this is VB. Of course, here we assume that VA is bigger than VB. Because if it is the opposite, like VB is bigger, these two never collide, right? VB always go further and further. So let's say we have this scenario, and now these two things collide. And after they collide, so they're going to bounce back. This is our assumption. And let me draw them one more time. This is the first one, and this is the second one. So after they collide, let's say they collide for a short time. So at the moment of colliding, let's say if they collide for this amount of second, delta t second, a small time. So there's going to be a force between them. And this force, you know, because of the Newton's third law, they are going to be same but opposite direction, action and reaction, right? So let's say this is F, and this is going to be also F. And we don't know their velocity. Maybe this guy gets a new velocity, and this guy, we don't know. Maybe it return back, or maybe move to the same direction. For now, let's assume that it goes to the same direction. But this guy, its velocity, let's call it V prime B, and this one is going to be V prime A. Okay, so this is the scenario that we have. So either scenario 1 or scenario 2, doesn't matter. These two collide. At the moment of collision, there is a force, action and reaction between them, and there is speed change, but we don't know how much, v prime A and v prime B. So let me see if I can use this formula that we just learned, that G1 plus F delta T is equal to G2 to solve this problem. By solving this problem, let's say we are interested finding out v prime A and v prime B. So I'm going to write down the formula here. So let's start writing everything for A, for particle A. For particle A, can I write MA VA plus F delta T equal to MA V prime A? I guess everybody agrees that we can write this, right? And for now, assume that this is all vectors. So we just don't write their direction. We assume that later when we want to put the numbers, we put their like positive and negative. And what about the same things for particle B? I can write down MB VB plus, not this time, plus. Oh, maybe we should be careful here. If the positive direction is to the right, so this is negative, the force, then for B it is positive. F delta T is equal to MB V prime B. All right, so pay attention because the force on the right for B is to the right and for the left is the opposite direction. So it is minus F. So I have these two formula, one for particle A and one for particle B. If I add them together, let's do that. If I add them together, what do I get? I get MA VA plus MB VB is equal to MA V prime A plus MB V prime B. So in fact, we show that for these two particles, whatever momentum they had before collision is equal to their momentum after collision. But still, we cannot solve this problem, right? Because we have two unknowns, V prime A and V prime B. We need another piece of information. Also, we notice that we don't know delta T and we don't know force. If somebody wants to find these, then he has to first find V prime A and V prime B, and maybe then he can measure delta T. So it's possible to measure it. Let's say we have our watch and we measure how long does it take for that small time that these two collide. Of course, it's not possible by a watch, maybe by a video, and then we look at the video later, because this time can be a fraction of a second or millisecond even. So as I said, we need another piece of information, which it comes to our help, something which we call it coefficient of restitution. We show it by E, and you saw it most likely in physics. So E is equal to V prime A minus V prime B divided by VA minus VB. And it doesn't matter how we write this, like which one is first, which one is second, because this value is always positive and we always calculate the absolute value. But we need to be careful. If we consider, let's say, to the right positive, then in this formula, for example, if I have VA here, just something for you guys to be careful. Let's say if I have VA here 10, VB here 5, when I'm replacing it, this formula, I put 10 here, and I put minus 5 here. So minus by minus is going to be positive, and then denominator, I'm going to have 15, right? So this is basically the relative velocity. Just be careful about the U and the sign. So This one, then we call it coefficient of restitution. So what is coefficient of restitution? It's a property which it depends on the material. Let's say this ball A and B, are they made out of steel or no, made out of rubber? Then they're going to have different E. For example, if they are made out of steel, you see this E is a bigger number, right? Bounce back very fast. But if it is, let's say, rubber, then they're not going to bounce back like a steel. So it depends on the property, and we can find it for different material on tables. It's more like, let's say, the friction coefficient. So it's a value that the question give this one to you. Now we can solve the problem. Okay, so I'm going to stop here and see if you guys have any question. So if we have two different materials, and that's in fact a good question. Let's say A and B, two different material, and also maybe different sizes. Let's say a big ball A and a small ball. There are formulas. If you Google Wikipedia, developed by, like they called Hertz formula, which you can put the diameter of these two particles, their material, because for each material, we have a value, which I hope by now you guys learned from your MEC 260, we call it module of elasticity. So A and B has different module of elasticity. We put all this value and we can find this E. But for now, we assume in this course for a question, E is going to be given to us. But in future, if you're solving a problem, you can always find that formula. And based on the material, find this E. Let's say steel and aluminum, right? So why VB is negative? So remember, this is all vectors, right? These velocities, for simplicity or out of laziness, we don't put these velocity sign, like this vector sign here. So now if you're solving for scenario number one, if you are considering, let's say, the motion to the right to be positive, right? Then VA is 10, VB is -5. But if it is for scenario number two, if this is 10, this is 5, then you're going to put 10 -5. Okay? I hope it's clear. Let me also write it down here, so later you guys can, when you look at the notes, so it's going to be 10 and -10. Maybe let's put it something like that. Case 1. And for case 2, it will be 10 and 5. Okay? All right. Any other question, guys, related to this? Sign of F. So these two, when they collide, there's going to be a force between them, action and reaction. And intuitively, we know if one force is to the left, its reaction is going to be to the right. So the same, we have F here to the right and F here to the left. So one of them get positive, one of them get negative. That's why when we add them together, they cancel out, right? But let's say if we solve a scenario like this. Let's say I have a ball, let's say maybe a wall here. So this is then a wall, a fixed wall. And then this particle or this ball comes and hit this ball. Let's say with velocity v, and its mass is m. Okay, it comes and hit this wall and it bounced back. Let's say move in the same direction, bounce back. So what I can write now, let's write it down here. Of course, I cannot do anything for the wall because we don't know its mass. Its speed is 0. It's not going to be that useful for us. Let's write down for B. So this is what I have. The way that I solve this problem in order to avoid any confusion is like this. And I suggest you guys do the same. I write down that let me find this guy. So I have this mass m moving in this direction by velocity v, plus then for a short amount of time, it hit the wall. And because of that, let me move this guy a little bit over there. It's going to be a force here. And as a result, this one is going to bounce back and let's say get to velocity v prime. Okay, so I have velocity f v, and then it hits the wall and then moves back. So this is then what is happening for the scenario. I have scenario 1 plus this, let's say colliding for delta t second. I'm going to write it down. So here, initial velocity or initial momentum to be initial momentum, then an impulse for delta t second, then we get to the second momentum. Momentum after bouncing, right? So if I want to write down the relation, can you guys try to write it down? What can be the relation for this? I'll just give you 10 seconds to think about it. Let me move this one over here. While you guys are thinking. So what can we write for this scenario? Maybe I should have allowed myself more room here. Okay, better. So this is what we have. We had a ball, m, velocity v, and it comes and hit this wall. So we have its initial velocity and it bounced back. Its velocity now is v prime. And we know there must be a force, F here. And it impulses for this amount of second, delta t. So the only relation that, I can write for this is that mv plus f delta t is equal to mv prime, right? So let's see how many unknown we have. We don't know the time, we don't know the force, and we don't know the v prime. The only things that we know is mass and initial velocity. Of course, from the material, whatever the material of the wall is, whatever the material of this ball is, I look it up on the internet and I will find E. And the question give this one to us, the coefficient of restitution. So wall is always its velocity is 0, right? It doesn't move. So then E is going to be V prime divided by V. And because we care about the absolute value, although like V is going to the left, V prime going to the right, we don't care, right? But to be exact, if we want to write it correctly, we should write it down like this. E is equal to absolute value of V prime minus V. Because V prime is to the right and V is to the left, negative. Okay, so we have E, but still we have two unknown. What should we do? We cannot still solve this problem. Any idea? So one more time, this is what we got, right? mv, initial momentum, plus impulse is equal to the momentum after bouncing back, mv prime. E is given to us, so this is given. The wall cannot help us because, in fact, this is the same problem as previous one, but the second mass, the wall here, is Earth, right? It's a gigantic ball, and its velocity for this problem we assume 0, so it cannot really help us. We still don't know F, we don't know delta T. So let me check chat and see if somebody has an idea. So can we solve V prime? Yes, we can solve V prime, but still we have two other unknown, force and delta T. Right? Let's say we are interested finding force. So in this problem, basically the only solution for us is to measure delta T. Right? So we need to measure delta T. If we measure delta T, if we know how long does it take, then the problem will be solved. Because remember, we have one equation here is E, one equation is this big one that we wrote here, but still we have three unknown, F, delta T, and V prime. So if we cannot do anything about force unless we build a very tiny advanced Wi-Fi sensor into this mass M, which is very difficult, but we can measure delta T. Okay, let's solve one example so then all of this makes more sense. I'll let you guys to read this example and then we will solve it together. And similar to energy method, this is like one key example. If you can understand and follow this example, then it means you are good for this topic and you can solve any other problem. So I'll let you guys to read and try to see, maybe you take a note, like try to guess how you can solve it. Okay, we have this lady, a tennis player, right? And strikes the tennis ball. So, and then maybe the ball is coming back with a velocity of V1. So this is V1. And then it bounced back with V2. But this time maybe because basically the racket is in an angle, it doesn't bounce back like the previous problem. Like if I move back one step to the previous slide, if let's say this wall was oblique rather than be a straight wall, then maybe after hitting this surface, the ball doesn't bounce back straight. It goes in an angle. Okay. But this problem, it's a little bit more advanced. It comes back, bounce back with an angle 15 degrees. So we have these two velocity. And also the coach measure the impact time, 0.02 seconds. So you see, it's a very small time. And also we have the mass as well. And what do we want to find out? We want to find out the force. It's important when somebody is designing a racket. Last year in one of my courses, MEC 305, one team of students, they analyze like different mesh for rackets and which one is the best. And in fact, they could measure the forces like using this simple formula and doing some tests. And this is very common, like this example that we're solving in a sport. When they want to design this racket, they do all this measurement to make sure what is the best mesh or the material for this racket to generate a bigger force, basically. So, but for now, let's just solve this problem and see how we can approach this problem. All right. So similar to the example of ball, always solve it like this, the way that I do it. Say that, okay, scenario number one, I have a ball. Let me draw it bigger. And then this ball is just moving with the velocity of v1. Then there is some force on it. So this is then the same ball. Let's say all right. And then after that, it bounced back. Be a little bigger. And after that, it bounced back. And let's say it comes here. Okay. And let's see what we have. We have here velocity v1, and then this will be velocity v2. It is in an angle. Maybe a smaller. It's just 15 degrees. Okay, and remember, we are just analyzing the problem at this moment, this 0.02 seconds. So all of them are at just one point, but I just draw them separately. Of course, you can imagine the ball 1 second later is going to be over there, but we don't care. We just analyze it for that moment that this collision is happening. So this is what I have initially, my velocity v1, and this is my velocity v2. It's important to draw the middle one correctly, the force one, right? And you need to carefully draw all the forces that you have. So first of all, when it hits this racket, it has both Fx and Fy in both directions. Because see, the ball is not moving straight, it's not bouncing back on horizontal. There might be some forces that lift these things up, right? Which we don't know, it might be zero, but we assume that since this ball is moving up, there might be some forces that move these things up. Let's call this one Fx, and let's call this one Fy. What else do we have? Are we consider everything for the forces here, guys? Or there is something that we missed? Take a look at this diagram and tell me if the diagram is correct. Oh, gravity. Thanks, Felix. We almost forget about one important thing, and that was gravity. So let's put this gravity here. And in fact, this is very important in the design of this ball and racket. So this is then mg. Okay, so our diagram is complete. And maybe I do one more step to make my life easier, and I find the component of this velocity. So if this is the vertical direction, then the component of this guy is going to be let me use a color that I've never used. Okay, this one. Okay, and what they're going to be, it's going to be this angle is 15, is going to be V2 cosine 15 and V2 sine 15. So if we draw this diagram correctly, we almost solve the problem. Just we need to know that the middle one is not a force diagram, it's the impulse diagram. So, and when we say impulse diagram, which means that all the forces has to multiply by the time. So it means this guy multiply by delta t, this guy multiply by delta t, and this guy multiply by delta t, which we happen to know the delta t, right? This is the question, give delta t to us. Now let's write things down. Everything on x and everything in y. So what do I have in x direction? In x direction, I have minus m v1. Again, let's assume that this guy is positive to the right and up is positive. So I have minus m v1. So this guy plus this guy gives us this guy, right? The first figure plus this, the middle one gives us the third one. Minus mv1 plus fx delta t is equal to m, mass is not changing, v2 cosine 15. What about the same things in y direction? So in y direction, I don't have any things to start with. Then I have fy minus mg multiplied by delta t, right? I just factor this delta t, so it's going to be like that, is equal to m v2 sine 15. Problem solved, right? We have all the information that we need. And simply from here, we can find fx Newton, fy something Newton, and f, the total force, is going to be fx squared plus fy squared. You can substitute these values later and find out the actual value. Now I'll let you guys to write the note, take a moment and make sure that you understand it. Again, if you guys could understand this problem, then that's great. It means you can solve any problem involves impulse and momentum. How do we know if the question related to impulse and momentum? The key things is this time, basically. When the question talk about time, this time for the impact, then we know it has to do something with impulse. And of course, in this question, we don't need to know the coefficient of restitution, but if the question asks us to calculate it, there are ways to calculate it, but it's not necessarily, and it's out of the scope of this course. So, and please let me know if you guys have any question. I'm gonna check the chat, the reaction force. So the reaction force, if you mean, the reaction force goes to the racket, right? So we just draw one side of these things. We don't care about the racket because whatever force Fx we have here is going to be Fx on the racket. Let me draw it maybe here so we don't get messy. So if this is the, let's say, racket here, the side of racket. So these things is going to have an Fx and Fy. Action, reaction, the opposite way. So it's going to be Fx, Fy, and this guy is the racket. Okay. But we didn't write anything related to this racket because we don't know any information for that. If the question, for example, gives us the velocity that this lady is hitting this ball or the mass of this racket, then we consider this one. But this problem, no. We just stick with the portion that we know we have the information. Okay, so let's now move to the last example of this topic, and we are done. I'm going to let you guys to read this one and try to understand and visualize the mechanism, by mechanism figuring out what's happening here, and then we'll solve it together. And while you do that, I'll also try to figure it out myself. So we have this simple assembly here. The question is telling us that it's a lightweight. So when it says a lightweight, it means that we ignore the weight of this rod. So this is what we do now, but next chapter we will solve the same problem and we consider the weight of this rod. But for now, it's because your focus is on particles. We assume that this rod doesn't have a weight. And then we have this mass 2m, this mass 4m, and then this putty, maybe it's a piece of dough or maybe a mud or something. It comes and stick to this mass 2m. So you can imagine if these things happen, as a result, this pendulum or this mechanism is, or this lever, whatever it is going to move like that. And it's going to rotate with a speed which, let's call it theta dot. Okay? So this is all the information that we have. So if this rod is moving by the speed of theta dot, it means, and quickly we can solve it, that this point has a velocity because it is on a circle, right? And it's easy for us now to calculate its velocity. Its velocity is going to be L theta dot. Do you guys agree? Because this point is rotating about point O and on a circle with the length is L. So it's a speed at L theta dot. What about the other side? This guy also has a velocity. Its velocity is going to be 4L multiplied by theta dot. Okay, so this is all the information that we have. And now we need to solve this problem. Can I write down that in this problem, because there is no friction, G1 is equal to G2? Let's see why. This mass M, it comes and hit this mass 2M, but they stick together. They're not going to separate. So whatever force is is between them, but we don't separate them. We consider them as a whole mass. Like after this guy comes and stick to this guy. Now this is all I have. So you may say, what about the weight? Because we have gravity, that's correct. In this problem, so first we can assume maybe this question should have clarified that this lever or this mechanism is on a table, not on a vertical plane. Otherwise, we know before this mass comes and hit these things, because this 4m is heavier, then everything is going to start rotating, right? But we don't know any information related to that. So then all I write is G1 is equal to G2. What do I have for G1 is M multiplied by V1, because the rest, we assume they were at rest. And then what do I get for basically scenario number 2 is mass M plus 2M, because these two on the right becomes one mass, multiplied by their velocity, and then plus other one, 4m multiplied by 4L theta dot. Oh, we missed something here. This guy has to be negative, right? If this is positive, then this guy has to be negative. So this is negative, this is negative. And can we find theta dot here? I guess we do. Question on the chat. So why the velocity on the left is, oh, sorry, my mistake here. It's 2L. I just confused these 4. So this is 2L, guys. Please correct it. Yeah, the distance is 2L. Thank you. 2L multiplied by theta dot. All right, so let you guys to take a look, and if you have a question, please ask. Let me also check chat. And thank you. We have to correct it also here. Not that one. $2L. And we are done. From here, we will simply find out theta. What the question asked, I forgot. So V1, so yeah, maybe theta dot, we can find theta dot. So we assume that V1 is given. Okay. So because it says it's traveling with the speed V1, let's say the question gives us the value for V1, the value for M, then from here we can find theta dot. Yep, that's simple. We can solve this problem. But this problem becomes a little bit complicated when this rod has a mass. And also it becomes a little bit more complicated when we have gravity. Let's say for now this thing is on a table, on a horizontal table, so the mass going into the screen, so that's why we ignore it. All right, guys, so if you don't have any question, we are done for today. Please review this topic. It's just these 2 simple examples, example 6 here and example 5 carefully, and all the formula that we wrote here. And you can also solve the rest of problem set 2 which you need them for this week for your quiz basically. The quiz for this week is going to cover work and energy, like the topic that we cover on Monday, the today topic, and maybe one question from what we cover on Friday, which is a very simple topic. Maybe or maybe not, but definitely impulse and momentum and work and energy. So question, what does M here represent? This M is the mass of this guy, right? The mass of this piece of putty or piece of mud or whatever, something sticky, and maybe a big gum comes and hit to this mass 2M and stick there. So at the, like initially all we had, initial momentum, this 4M doesn't have any velocity multiplied by 0. This 2M doesn't have any velocity, is multiplied by 0. And then the only things that we have is this mass M equal to V1. This is all we have for G1. What about G2? This is what we wrote here. So these two mass, M and 2M, now are together. What is their velocity? Is L theta dot. Is 4M, it has a mass 4M and its velocity 2L theta dot. You need to be careful about the direction. So like always, coming down, I show it by negative, and going up, I show it by positive. One more question in the chat. All right, so you're good. So, all right, guys. So I see you on Friday. Please try not to miss the lecture on Friday. It's a new topic. We're going to start talking about rigid body, degree of freedom. It's an important topic, and you'd better be in the class. So if you have a question, you can ask, and so everything be clarified before you leave the class. I'm going to stop the today lecture and also stop recording.